Lesson 5. What is a sample? In statistics, a sample is that part of the population from which data has been actually collected. The particular members of the population that were selected to be included in the sample are called the subjects. When sample data are used to determine some aspect of the sample, the result is referred to as a statistic. For instance, according to a sample of Sierra College students, 1.3% of the sample of students had red hair. This result, 1.3%, is a sample statistic. The sample size is the total number of subjects belonging to the sample. In statistics, the sample size is denoted by the symbol lowercase n. The sample size n is a statistic. For instance, a sample of 153 Sierra College students was taken to observe student hair color. Thus, n equals 153 for this sample. In statistics, a particular sample data value is denoted by the symbol lowercase x sub I. When a sample is collected, the data values from each and every subject of the sample is denoted by lowercase x sub 1, x sub 2, x sub 3, so on and so forth, through x sub lowercase n, where lowercase x sub 1 is the very first data value in the sample, and lowercase x sub n is the very last data value in the sample. Different notation is used throughout statistics in order to distinguish population values from sample values. It provides a means to communicate results that are based on a census, which are parameters, from results that are based on a sample, that is statistics. To illustrate this concept, let's consider the following population, where each and every member of the population has the following data values. If a census was conducted, each and every one of these data values would be collected, and the result based on these data values would be a parameter, and that parameter would give a very specific result. But when a sample is collected, only part of the population is collected. So the sample only consists of that part of the population from which the data values were actually collected. So in this particular sample of 6 data values, only these particular population values were observed. And then the result based off of these particular data values would result in a statistic. Since the statistic only includes these population values and not every population value, the result we get in the statistic is not necessarily exactly equal to the entire population. In fact, if a different sample of 6 data values was collected from the very same population, it's most likely that we'll get completely different population values in the sample. Thus, the statistic calculated based on this different sample is probably going to be different than the statistic based off of the other sample. So when different samples are collected from the very same population, you can expect to get different data values, thus resulting in different statistic results. Since a sample involves data collected from only part of the population, a statistic provides results which are not necessarily equal to the parameter. In fact, distinct samples selected from the same population will most definitely include different members of the population. As such, different samples will produce varying results for the same statistic. So, with samples, there is some uncertainty involved. But not all is lost. In statistics, if appropriate methods of sampling are applied, this uncertainty with sample results, called the margin of error, can be measured. This margin of error can then be factored into the final results of the statistical analysis. In order to achieve accurate, reliable, and valid statistical results, it is imperative to collect a representative sample of the population. That is, a sample that exemplifies or reflects the attributes and characteristics of the population it was drawn from. representative samples are regarded as unbiased. When a representative or unbiased sample is drawn from the population, the results observed in that sample can be generalized back to the population of interest. In other words, with representative samples, the resulting sample statistic will reasonably reflect the corresponding population parameter. Therefore, valid results can be achieved when representative samples are obtained. On the other hand, when a biased or non-representative sample is drawn from the population, the results observed in that sample are not valid and should be considered unreliable. In statistics, when collecting sample data, the primary concern is the quality of that sample. The utmost attention needs to be given to employing an appropriate method of sampling that would reasonably ensure the attainment of a representative sample. Only after the issue involving the quality of the sample has been addressed, the matter of quantity of the sample or sample size should be determined. If the method of sampling used produces a biased sample, it does not matter how much data is collected. The results are not valid. If the method of sampling used produces an unbiased sample, with regards to the matter of sample size, in general, bigger is better. That is, more data provides more information, and with more information, the sample results will become more accurate and reliable. There is no single correct exact amount when it comes to sample size. Instead, statisticians adhere to the following principle. Select a sample size that is sufficiently large so that the true nature of any effects will be revealed, but not too large so that the sampling process becomes too impractical, time-consuming, or costly. So, what constitutes a sufficiently large sample size? Well, when a representative, unbiased sample is obtained, a sufficiently large sample size may not be as large as one would think. To illustrate this concept, I'm going to show you a picture and ask you, what do you see? Now this photograph contains millions of pixels. Well, 1,315,840 pixels to be exact. But I'm not going to reveal the entire population of pixels to you. I'm going to reveal a representative sample. So here, I've taken the entire photograph and broken it up into 35 regions, representative of the entire photograph, from left to right and top to bottom. And only one pixel from each of these 35 regions was collected. Therefore, the color for that region is only representative from one pixel. So, based on a sample of 35 pixels, can you tell what this is a picture of? Probably not. We'll need more data. So, here is a sample of 80 pixels from these millions of pixels. Again, representative of the entire photograph, from left to right, top to bottom. Is a sample of size 80 big enough for you to see what's going on? Probably not. So we'll need more data to be more accurate. Here's a sample of 154 pixels. Only 154 pixels is relatively small compared to the millions in the population. But even though it's a relatively small sample size, at this point we have an idea of what this is a picture of. It's probably a photograph of a person. But who that person is isn't exactly clear yet. The margin of error is too big. So we need to collect a bigger sample size. Here's a sample of 357 pixels, just a few hundred. Can you tell who this is a picture of? Maybe some of you have an idea. But just a few hundred is good enough for you to have an idea, but maybe you're not exactly 100% sure yet. So let's take a bigger sample. Here's a sample of 720 pixels. Now do you know who this is a picture of? Probably many more of you looked at this and said, oh, I have an idea. So when you're dealing with representative samples, all you need is just a few hundred or several hundred to have a good idea of what's going on. You really don't need thousands and thousands of data values in the sample to see what's going on, as long as the sample is representative. But still, the margin of error may be too big for you to have enough confidence to really state who you think this is a picture of. So let's take an even bigger sample. Here's a sample of 1,620 pixels. Now do you know who this is a picture of? I'm sure many of you definitely have an idea now. And those of you who had an idea before, it's only confirmed your original idea. So as long as you get a good representative sample of a few hundred, maybe up to 1,000 or so, you can have enough data to really see what's going on. At this point, collecting more and more data just costs us more time, energy, and effort. Yes, the margin of error will get smaller, our result will get accurate, but is it worth spending that extra time and effort to get that type of result? Here's a sample of 4,061 pixels. Definitely confirmed the idea who this is a picture of. You can confirm it even more with an even bigger sample, in this case 9,138 pixels. Or an even bigger sample, 20,560 pixels. Or even larger, 52,634 pixels. But all the extra energy and work required to collect all that extra data didn't really change the original idea or result of who we thought this was a photograph of. So bigger is better. That is, more data gives you more information. The results are more accurate. But there's this point of diminishing returns where you really don't have to collect that big of a sample. Just a sufficiently large sample that is representative of the population to get a good idea of what the true results are. Here's the sample of 146,240 pixels. And here's the original photograph of all 1,315,840 pixels. So this was a photograph of Abraham Lincoln.